constitutes a cloud-ready application. We are going to talk about why you should bother, why should we do this, and then we're going to talk about cloud migration. So, what do you have to do to migrate something to the cloud? We're going to talk about some cloud migration patterns, and then we're going to kind of go up the ranks. We're going to start with code level patterns that we can talk about. We're going to go up to architectural patterns. These are things that you can do in your architectural practice. And then we're going to cap it off with some DevOps tips. At the end, you'll have some resources, and you'll have a bunch of different things in your tool belt to help you build applications that run well in the cloud, run well in your data center, run well pretty much everywhere. It's good stuff. So what does the cloud mean anyway? The cloud. It's this kind of silly buzzword that people come up with, but really, like, if you look at it from a definitional standpoint, there are 5 different things that constitute what would be considered a cloud resource. This comes from NIST. So the big one is on-demand self-service. So instead of sending a ticket and waiting 6 weeks for some jabronis to go push a bunch of buttons for you, you as a developer can run a pipeline, you get your service, you can go. On-demand self-service. Rapid elasticity. So instead of having to, fire up the old phone call and have Dell mail you some more stuff, you can push a slider bar and get more capacity. This capacity is based on a pool of shared resources. So we think about Azure, AWS, Google, whatever. Really, it's just a bunch of servers that they give you a little slice of. So you have a pool of shared resources that you can elastically provision into. Metered usage, that is, your service is metered. So whether it's vCores, gigabytes, gigaschlocks, or whatever weird unit of measurement your cloud provider comes up with, you have a metered usage. So you can control how much resource you consume at kind of a micro level. And then finally, it's all accessed over the network. And the thing about this definition of the cloud is that it includes a lot of different things. So obviously it includes the public clouds that we all talk about. Usually when your company is like, we're going to go to the cloud, usually that means they're going to go to a public cloud. And the public cloud companies are going to spend a bunch of money, take them out to dinner or whatever to try to get them to go to their particular cloud. But that doesn't necessarily constitute the totality of what is a cloud software offering. So you have private clouds. So all of the cloud providers, the big ones anyway, have a private offering. In Azure, it's called Azure Arc, AWS Outpost, there's other ones. So this is stuff that you can run inside of your data center. And then there are a lot of hybrid cloud options. So these are things that you can either run inside of your data center, or there are usually offerings in your cloud provider that you can run them on their cloud if you enjoy paying for things twice. But if you want to run your own cloud in your own data center, that's totally doable using things like OpenStack, OpenShift, Pivotal. I know somebody who works at a big financial company, and they are really successful using Pivotal Cloud Foundry. So there's a lot of different options. The OpenShift, I've seen companies use OpenShift internally. And you can also have a hybrid situation where you have your kind of dedicated capacity, and then you can kind of shell out to the cloud and have additional flexible capacity using these hybrid solutions. So it's not just public cloud provider. Really, the cloud is those aspects we talked about a slide ago, having the rapid elasticity and all those other things. So, and what that means for you as somebody who's building cloud-ready apps is that means even if you're not going to a public cloud provider because your network staff is insecure about putting everything out in the open, you can still have most of the benefits of a cloud provider using one of these other pieces of software. And why bother? Why should we care about running things in a cloud-friendly way, even if you're not going to go to a public cloud or the cloud at all? One, cloud-ready apps run better everywhere. If you build using these various design principles we're going to talk about, your app is going to run better even in your data center. Even if it's running an IIS on some server with 30 other apps, it's still going to be better than an app that doesn't include these various things. Specifically, they're easier to scale. So one of the advantages of building things in a cloud-ready way is that you have scalability built in, because pretty much everything in the cloud is built to scale. And ultimately, they're more maintainable. So if you especially in the sort of DevOps tips and automation area, if you build these automation things, you're going to have apps that are easier to maintain. And what you're going to find is that what constitutes cloud ready has a pretty hefty overlap with what's just considered building good modern software, and that's okay. So with that, let's talk about cloud migration. So in the world of cloud migration, there are 5 patterns. They all conveniently begin with the letter R. So it's one of, I remember, has anybody ever seen the meme where you have the mnemonic to recommend you ever seen the meme where you have the Great Lakes and you have the mnemonic to remember them, and it's like Letty licks lettuce lightly, because everything starts with L. This is the same kind of deal. I just wasn't creative enough to come up with a mnemonic that starts with R. But we have a couple different patterns. The one that's pretty common as kind of a first move out of the gate for companies is the old rehost, aka the lift and shift. Beyond that, we have refactoring. So this is where you can lightly refactor your application and throw it into something like a PaaS service, so your Azure App Service or your AWS equivalents, whatever that is, or containers. And there's about 1,000 ways to run containers in pretty much every cloud provider. There's a famous blog post by This Week in AWS where it's 17 ways to run a cloud container in AWS. And I'm pretty sure Azure has at least half as many of those. If you want to go beyond your refactoring, you can re-architect your application. This is a little bit more of a major project where you take your domain logic and you shell that out into either services or some other pattern. So this is more of a bigger lift. And this is something you'll see with a lot of legacy applications. So if you have a big legacy monolith, people will start shelling out microservices. Done that a couple of times. And then, of course, at the end, you have rebuild. So just rewrite the thing. So if you have something like hanging out on a mainframe, you're probably due for a rewrite. And then, of course, the easiest cloud migration pattern is to don't and just retire the thing and just shut the thing down. So if you don't need it anymore, that's probably the best thing to do. And when you're looking at a cloud migration, generally you build an app catalog, you go through all the different applications, and you kind of identify which one of these groups those apps are going to go into based on the maturity of the application. So for example, if you're building like a modern .NET Core app, that's pretty ripe for a refactor because those generally are built to run in a cloud-friendly way by default. Whereas your legacy .NET application, you might what?
Sorry.
Oh, sorry. Might be a little bit more towards the refactoring end of the scale. And the thing is, each of these patterns has a cost to migrate and then a cost to run in the future. And the easiest thing to do is the lift and shift, which is why a lot of people do it out of the gate, but that is the one that is the worst to do, because what ends up happening is you go from paying for cheap VMs to renting expensive VMs, and you basically throw away 90% of the advantages of going to the cloud. So if you are running in Azure and you're renting VMs for your stuff, the same way you're doing it in your data center, not ideal. It's not the way to go. Meanwhile, your refactor, re-architect, rebuild are increasingly expensive, but because you're building things in a cloud-friendly way, they'll all be roughly the same relative cost to run. And then obviously retire is easy and doesn't cost you a thing because it doesn't exist anymore. And you, as a developer of cloud-friendly services, you want to live here. You want to refactor your applications. Because obviously lifting and shifting is not good, but if you develop an application that's pretty nice and easy to refactor, you can usually get away with a light, cheap refactoring and end up rehosting, and ended up getting to move that to one of the cloud services of your choosing. So this is the goal. And with that, let's talk about how to design your apps in a way that is actually easy to migrate. And we're going to start at kind of the code level, and then we're going to zoom out and go to the architecture level, and then we'll talk about DevOps at the end. The number one thing you need to do is make sure you're using dependency injection. You should be doing this anyway. More specifically, you really want to abstract your infrastructure dependencies. So in your code, you want to avoid any hard linkages to file systems, messaging systems, databases, anything like that, any kind of data store. So you want to hide those things behind abstractions, because when you go to the cloud, those are the things that are going to change. So if you're using a local file system, for example, that's a high high priority for abstraction, because when you go to the cloud, you're going to be using a storage account or some other thing. You're not going to be using a file system on a machine, because that's just not how you build applications in the cloud. At the architectural level, if you want to go even a step further, you can abstract out your infrastructure using something like Dapper, but that requires a bunch of other architectural choices to get there. But until you can get to that point, or if you can't get to that point, abstraction, just standard dependency injection, will do okay. Configuration. This one's a little bit of a mind bender, but generally in cloud applications, you store your configuration in the environment of that particular build machine. So instead of having text files that are deployed with your application, you generally use environments as your configuration, and then your variables come in. This is super easy to do in .NET. There's a built-in environmental configuration provider that will read your environment variables and will do well. Locally, you can use local secrets though, but as a general rule, the whole .json file thing that's kind of the standard is not what you do in the cloud or in more modern cloud-based applications. How many people are using the JSON configuration in their app? I'm not seeing a lot of hands. Okay, what are you using, like configuration services or? Okay, cool. Statelessness. You really want to avoid statefulness in your applications. So generally what that means is that you don't want to rely on your services hitting the same machine over and over again. This is kind of the default in modern .NET applications, but it's not the default in a lot of more legacy applications. And specifically for us .NET developers, that means using a distributed cache over a memory cache, because memory cache is specific to the machine, and you want to avoid that, assuming you're using a caching layer at all. So there's a bunch of different options, whether it's Redis, SQL Server, or other solutions. There's a lot of ways to do distributed cache, so pick one of them. Resiliency. So one of the things about building stuff in the cloud that on-prem developers could take advantage of is that in the cloud, you tend to achieve resilience by having lots of units of things that are kind of transient. So instead of having like one server that you really care about and try to maintain, you're running a fleet of Docker containers in an orchestrator, and if one of them blows up, who cares? We'll just spin up another one automatically. And so one thing that you can run into is when you're building stuff in the cloud is you have a lot of transient faults. So a lot of times you can have like a blip, something will just not work, and then you just try it again and you'll be fine. Additionally, a lot of things go over the network in the cloud as opposed to everything happening on one machine. So you have the network faults to kind of add to the fun. So you want to build resiliency patterns into your code, and you should be doing this in general. And the easiest way to do this in the .NET world is to use a library called Poly, which has this lovely festive parrot mascot. And so there's a bunch of different patterns that are easy to do. The first one is retry. So the thing about retries, though, is that you don't want to retry forever. So you need to have some sort of timeout. Additionally, you don't want to retry at a consistent cadence. So you don't want to retry like every second, because if you have a bunch of stuff hitting a service and it's falling down and then you have everything retry every second, you're going to cause the same problem. So in your retry pattern, you want to build in an exponential backoff. So you hit it, you retry kind of immediately, and then you build an increasingly longer delay until you hit the max retries. So like a quarter of a second, half a second, 3 seconds, whatever. Another thing for retry patterns too is instead of having those consistently at those intervals, you also want to add in a little bit of randomness. So instead of having it be like an even like 250, 500, 1000 millisecond timeout, have each of those, but then add a random number of milliseconds from like 1 to 200. And the reason you do that is because that'll stagger the retries, so you don't end up in a situation where, similar to running it every second, you're running a group of requests all at the same time. Circuit breaker. So this is if you have a long-running process that's clogging up your system, you want to be able to blow that up. So use cancellation tokens to do that. So you don't want to have stuff stick around for a long period of time, because generally after a certain number of seconds, your users aren't going to care anyway, and it's better to just start over again. Caching. Caching is generally a good thing, but caching also adds complexity to your application. The thing about all these resiliency patterns is they're not something you should just blanket apply to your application. These are things that you kind of need to design out and think about for the various requests. And you can combine all these and get kind of, you can get a lot of different things like Netflix, for example, will run like half of these patterns in their workflow. But everything has a trade-off. Specifically with cache, it will improve your performance generally, but you need to be careful about what you're caching. You need to be careful about what layer you're caching at, and you need to be able to invalidate that cache at the right time. In the .NET world, I recommend using distributed cache because that's relatively easy to invalidate, and of course, it is stateless. Bulkhead isolation. So this is where one thing in a series of requests does not blow up your whole system. I'm actually running into this right now. We have we have an application we're relying on APIs and we're pulling multiple things in, and one data error in that grouping is blowing up our whole requests. So we are encouraging our API downstream friends to add a little bulkhead isolation to their stuff. And this is at more of a system level too. You want to make sure that a single group of faults isn't going to ruin your whole day. And then finally, fallback. So if you run into a problem and that problem sticks around, you want to have some sort of graceful fallback, whether that is a degraded experience or whether that is a message to the user to have them come back and try again, or some other sort of useful bit of information. You need to make sure that you run through your error states. This is something that I think developers, we tend to forget about because everything in our world is, we always go for the happy path. And I think a lot of times in systems design, we tend to forget to run in and detail all of our error states and come up with good messages, which honestly, as a user of software, to me is kind of a make or break. Like, I hate it when, like, how many of you had a situation where you're using an app, it blows up in your face and you get some completely incomprehensible error message and it just pisses you off. Not fun. One thing you want to do is you want to design for performance. In an on-prem app, generally performance kind of takes a back seat to a lot of other things. And the reason for that is because your scalability is more of a step function. So for example, if you're running an app and you need to increase your capacity, you get another server. That bumps up your capacity at a kind of a step function level. And if you're only using like 40%, you're not going to worry about optimization. In the cloud, it pays a lot more to be performant, because the thing about cloud applications is that everybody has the demo where it's like, oh, we can increase capacity whenever we want. That's cool and all, but that's not the magic of the cloud. The magic of the cloud is when you move the slider bar the other direction and you reduce the amount of capacity you're consuming to match what you're actually needing for your users. Because if you just crank things up, obviously you're going to waste a ton of money. And if you want to be cost efficient in the cloud, you have to be able to scale down. So all these different performance things actually begin to matter a lot more, because every couple of percentage points of performance you can get is less capacity you can buy, because it's metered. There's a couple patterns to specifically look into, specifically around the database. So you're going to be looking at the busy database. So in a lot of legacy applications, you tend to have a lot of logic in stored procedures, and you kind of just use the database as a service. Generally, this is a bad idea for things that run in the cloud, because those DTUs are a little bit more expensive than running the capacity on just a normal like PaaS server. So you want to avoid using your database as anything other than a store of data. Another problem that you run into is something called chatty IO. So this is where you bring up a page and you make a lot of little small requests in order to get data on that page, which is fine, except that each of those requests have overhead. And of course, the opposite of that problem is something called extraneous fetching. So this is where you send in a request and you pull out a whole bunch of data, but you pull out more data than you need. The most egregious example I found was during a project where we were doing a 14-hour-a-day death march, and there was a page that took 5 minutes to load for 10 items that had about 6 fields. And we went and looked at the code for that, and we looked at the database calls, and turns out what was happening is the guy who developed it was fortunately in another state because problems would have ensued otherwise, that I was that far away from him. But the nice thing is that it turns out he was an enterprise Java guy who really liked refactoring. And so every one of those items in the grid was a fully hydrated graph of the particular entity that was coming back. And each of those entities was created by a model builder. And that model builder for each one of those things did about, 15 database calls to pull in about 60 fields for each of those records in a 10 record grid. So you were looking at, 150 database calls to bring up 30 pieces of information. I don't know how it was a problem, but it was a problem. I don't think that guy tested his code because I don't think that would have been acceptable. I don't know. It was a bad day, I'll tell you that. But it was a much better day when we got rid of all those extraneous requests. And fortunately for that guy, I have never had to work with him again. Thank you. Another thing that you need to do in the cloud is you need to async all the things, specifically anything that talks to a network and anything that talks to data. You're going to waste a lot of compute cycles, which are charged, in a metered fashion, waiting around for stuff to come back. So make sure you keep everything asynchronous. Very easy to do in .NET. I've gotten a ton of mileage on just general performance remediation by just using basic async. I ended up on a team once where, you ever seen the cartoon when you were a kid where the guy drinks all the explosives and explodes, and he's like, it's a really cool trick, but I can only do it once. Somebody did that with software. They built this huge actuarial process, ran it once, and blew up production for about 24 hours as the thing chugged along anemically. And so the solution, of course, was, we'll just throw more CPUs at it and put it in the cloud. And that did help in the end, but what really helped was walking through the code and getting rid of all the synchronous data access it was waiting around for while doing that. And we ended up taking a process that worked 0 times at 24 hours to a process you could run in about 15 minutes. Not bad. And it's not like we threw a mountain of cores at it. It was a Kubernetes cluster with 3 servers. So it's not like it really needed capacity. It needed to be asynced and performance optimized. So you can get a lot of mileage out of that traditional, just traditional performance optimization and paying attention. Be mindful of logs. If you like spending money in the cloud, a real easy way to do that is to log a lot of data. This is something, especially at least in Azure, I know I've gotten burned on projects by excessive logging in App Insights. Turns out they charge you by the gigabyte. So make sure that you, make in lower environments, log more because you need the data. But in upper production environments with high traffic, make sure you turn it down as much as is reasonable. So you don't want to be running verbose logging in prod. And you want to be a little bit more careful about what you're throwing into your logs, especially when it comes to things like exceptions. I was on a project where we had an infinite kind of crash loop happen. And turns out the log, we got a message a couple of weeks later about the multi-$1,000 logging bill. I was like, the cost of this went up. I wonder why. And it's like, oops, logging. So be careful about logs. They can really burn you from a cost perspective. And this also applies to on-prem, especially if you're using something like Splunk or some of these other on-prem logging tools. Those also charge by the gigabyte, and this is a real good way to burn a lot of cache. So with that, any other questions on code patterns before we go up a tier, or any comments or things you want to throw in? This can be conversational. I don't need to stand up here and talk for an hour without interruption. Feel free to throw out questions if you want. All right, cool. Let's move on. So we're going to take it up a level. We're going to architectural patterns. Much like in the code level, you want to make sure you're isolating your dependencies. There's like a million different names for this in architectural pattern lingo, whether you call it onion architecture, or clean architecture, or hexagonal architecture. The thing you want to do is you want to keep your domain business logic at the center of your application. Beyond that, you want to serve it up using application services, preferably using APIs, which we'll talk about a little later. And then you want to make sure all of your like hard dependencies on either infrastructure or specific frameworks kind of live outside of that. So you want to separate your business logic and your plumbing. And the reason you do this is because in the cloud, it's easy to swap things out. But if you ever end up doing a re-architecture, if you have everything in nice domain services, you can just pull those domain services out, put a new front end out of them, and off you go. It makes it a lot easier to kind of plug things in as you need at a dependency isolation level. And then just to kind of like, we're going to rewind a little bit and have a little bit of a history lesson. A lot of the things that we talked about up until now come from this thing called the 12-factor app framework. Has anybody heard of a 12-factor app? Okay, so a couple people. So this was invented by a company called Heroku. Heroku was an early provider of what would later become PaaS services. So basically, if you had like a Ruby on Rails app or a Node app and you wanted to just get it up into production without a lot of effort, you could fire up a Heroku service and they would host your app for you on the cheap. And what they decided to do, to find people at Heroku who like selling cloud services, created this 12-factor app framework to basically tell people how to make stuff that runs really well in Heroku. A tradition which has definitely been carried on by our friends at Microsoft and Amazon and Google, who have extensive documentation on how to write stuff that works well in the cloud, which is really high quality information. We'll talk about it later. I'm not going to go through all of these 12 factors because some of them are super obvious and other ones are built into the software system or built into things. Like the first one is having a code base and using source control, which if you're not using source control, you're probably not talking about going to the cloud. But beyond that, just generally, a lot of these things around dependency isolation, building stateless services, some of the DevOps things we're going to talk about, all come from this 12-factor app framework. But one of the misconceptions of this framework and people who want to adopt it, and just people who want to adopt the cloud in general, is that this only applies to microservices architecture. So there's a lot of, I think we've kind of come around on this one with the monolith versus microservices. But there seems to be a misconception that we found at certain clients and certain people that in order to run in the cloud, you have to run a microservices architecture. And that's not even remotely true. Monoliths are dope. The cloud will run them just fine. And you can apply pretty much all of these patterns to a monolithic application. You don't have to do microservices, regardless of your definition of microservices. And the thing that people don't fully realize about microservices as an architectural style is that they are not meant as a right way to do architecture for any project that you need. Microservices are an extension of something called Conway's Law. How many people have heard of Conway's Law? Okay, so a few more people. So this is a law that basically states that in an organization, the way you design your teams will determine the way your software is designed. So in this example, let's say we have a front-end, middleware, and a back-end team. Your architecture is going to look like front-end, middleware, back-end. Whereas if you break it down into more of a customer-focused thing, you will have your team boundaries be more vertically sliced. And the reason that people adopt microservices is that in larger organizations, and the same thing goes for MFEs and other forms of separation, is that large organization where you have lots of developers, you can isolate your code into independently deployable chunks so that those teams can be productive and flow without having to rely on other things or blow other teams up in the process. But the thing is, if you are running a team of 5 people, you don't need to do this. A monolith will do just fine. Additionally speaking, the whole boundary issue around a monolith is very hard to determine at the onset of a project, and generally it's a bad idea, which has happened on multiple projects I've been a part of anyway, to start with microservices because you don't know where those boundaries really should lie. Any questions on that? We got your standard microservices rant. I feel like in general though, if Twitter and developer media is any indication, I think we've rounded the bend of microservices are always good because they're not good or bad, they're just another pattern and they don't matter for cloud adoption. One thing you should do, though, is you should build your applications as APIs. And this comes from something called Steve Yege's platform rant. This is another little bit of history. This is one that's, if you want to laugh, Google this. I'm not going to read this to you. But basically, Steve Yege was a guy who worked at Amazon, went to Google, and basically the crux of the rant is that Amazon sucked at everything except this one thing. And Google was good at everything, but they couldn't figure this out. And Amazon had a layer of success that they didn't. And so basically, the ideas he talked about, this is a mandate from Mr. Jeff Bezos about how they should architecture things at Amazon. And we'll go to the next. Did everybody read that first slide? Okay, and we'll wait for this one. I'm not going to read the slides to you. Though I will read the last line because apparently it's covered by the Teams app. The last line is, anyone who doesn't do this will be fired. Jeff Bezos is not a nice dude, apparently. But the reason, when he says make it an API, they really do mean everything. Like the origin of AWS as a platform is the fact that all of their storage and cloud services had to be accessible as APIs. So not only is it fundamental to what you should be doing in your application, it's fundamental to the cloud as a whole, is making everything accessible via APIs. And that gives us a few things. One, it helps with keeping major components loosely coupled. Loose coupling is kind of the major point of any kind of useful architecture. It enables platforms. So right now I'm working on an application where they built a series of APIs. They were doing microservices when we started, and we were able to add a Teams modality relatively easily, at least in a couple of months, onto a fully featured web app because they built everything as APIs and we could just use their APIs. If they didn't design it that way, we would be in for a much longer slog trying to recreate all that functionality by building services directly. Actually, what would happen is we would have to build the APIs for them, which, because the company I was working with did the APIs, they were able to create a platform. And the thing is, even if you're building a monolith, building your monolith domain services as a set of APIs that you can reference is just generally a good practice, especially if you're going to go downstream and later on shell out into services at a later time. But how many people have built an n-tiered architecture? This is basically what that is on a monolithic level. Super common. Scaling, when you scale your software, how many people have played StarCraft before? Okay, you want to be like the Zerg. So in cloud world, we tend to scale out versus up. So we tend to scale a lot of small units of compute versus using, increasing the size of those units of compute to handle larger tiers of data. This is not as common in data centers. I feel like in general, you tend to increase the size of your machines if you're running VMs in a data center before getting more of them. In the cloud, we kind of do things differently. So building software that can easily scale out, i.e. is stateless, is very important. And finally, you want to design for evolution. So when you build your software, you want to build it so it's resistant to change. And a lot of things we talked about today are specific ways to make your software resistant to change and make it easy to evolve through the various stages of software development. Like a big reason we do domain-driven design, a big reason we do loose coupling, a big reason we do automated testing is to reduce the cost of change so you can evolve your software over time and you don't have to blow it up and do a whole rewrite. You can just re-architect and refactor your way along. Any questions on architecture before we move on to the next section? All right, cool. So we're going to finish it off with some DevOps tips. And the reason DevOps is important is because, when we say cloud transformation, what we really mean is DevOps transformation. Because the thing is, all of the advantages we get of, by using the cloud are really things that are part of the broader DevOps movement. The cloud, to a large extent, is really just a series of technologies that people made in order to deliver software at a faster, more flexible pace. So this is something that we tend to forget, or companies that I've worked with have tended to forget when they move to the cloud. They just want to recreate their on-prem stuff and their on-prem culture in the cloud, which is decidedly suboptimal. So what you want to do is if you're going to the cloud, you want to adopt DevOps principles. And the thing about DevOps is that we can have a lot of discussions over the exact definition, but the reality of DevOps is that it is a series of practices and patterns that revolve around 3 pillars. The first pillar is people. People are the most important part of the DevOps process, and creating a good culture, one that is generative, that focuses on learning and experimentation, that doesn't have blame, that has a high degree of psychological safety, that seeks and integrates customer feedback and talks with the various stakeholders, is extremely important. From a process perspective, we want to have lightweight, streamlined processes. We don't want to have to write 5,000 tickets to get your stuff into a production environment. We want to streamline that as much as possible because we want to go fast. We want to be able to experiment. We want to be able to visualize our value stream so people know what folks are working on and can see where they're going. And you want to work in small batch sizes. From a technological perspective, which we're going to talk about most, in this talk, we want to have, use cloud infrastructure, whether it's on-prem or public, doesn't matter. You want to have good build automation, continuous testing, and you want to have your loosely coupled architecture. There's more patterns and practices that fall under the DevOps umbrella, but generally speaking, DevOps itself are these practices, and cloud technologies are under that. So if you have good DevOps, it's relatively easy to move to the cloud. If you don't have a good DevOps culture, moving to the cloud is expensive and difficult because you have to undergo the cultural shift in addition to learning a stack of new technologies. Within that, you want to make sure you're audited. So specifically for our purposes here, as building a cloud-ready application, you want to make sure your builds and releases are automated. You don't need to be copying files off of your machine to get a build into prod. That is not ideal. And specifically from a pipeline perspective, there are 3 primary pipelines that I build with pretty much every project I touch. That's going to be a build pipeline that integrates the code and builds it, a gate pipeline that runs all of your automated tests, linters, etc., on things that are going to be pulled into your main branches, and then a release pipeline that's separate from your build pipeline to actually send your code out to the various environments. Sometimes they call this CI or CD, but those terms have a little bit more baggage than what they talk about in Azure DevOps, so I'm going to stick with pipelines. If you want to walk down the path, that's sort of the end ideal state where you can continuously integrate automatically and then automatically deploy to pipelines or deploy to environments after running through a series of tests. I don't see a lot of companies that do that, at least in upper environments. I always try to automatically deploy the lower ones whenever I can get away with it, but most companies want to have some sort of approval gate before releasing to production or upper stage environments, which is fine, which is technically not continuous deployment, but it is an automated build and release, which is still good. Nice to haves are having security scans, whether it's a SaaS tool like Checkmarks or trying to think of the other ones. There's a whole bunch of them. Or alternatively, having ETD, also having things like regression tests and smoke tests built in your pipelines are good, nice to haves. I don't get to build those on all the projects I'm on, but I've definitely built them in the past. Security scans are becoming increasingly common, though. Most of the companies I work with have some sort of SaaS tool that they try to integrate into their processes, and some of them have also sort of borderline like code quality SaaS tools like SonarQube, but generally those things are separated from the security-focused tools. That being said, it's good to have static code analysis just to catch the obvious stuff. Release early and often. Releasing should be like voting. You should do it all the time, early and often. The thing about releasing early and often is that you're going to reduce your cost of releasing. So if you do it all the time, it's going to become easier. It's going to encourage you to automate things, which is good behavior. And it's also going to decrease your batch size. So if a lot of small things being sent up continuously is going to be a lot less error-prone and destabilizing than large releases that have a large number of changes. So you want to release early and often as much as possible. So if you're doing releases every 3 to 6 months, that's you want to try and get that down to ideally whenever you have a change, but more realistically once a week or once every other week, along with your sprint cadence. Build a bed of automated testing. So this is something you kind of do over time. You can't like big bang bed of automated testing. But while you're developing, obviously do your unit and integration tests. Try to get good coverage specifically of business focusing functions. And then as you build your project out, try to incorporate some E2E, smoke, and performance testing in your application as well. The thing is, like these upper sort of more deployed tiers of automated testing, you don't necessarily want to hit full coverage because those are more expensive to maintain, but having a good suite of tests is really nice. Specifically around the API, I find that using Postman is a really convenient way to do that, and you can either run your tests in Postman or you can run them in your build pipeline with tools like Newman, which can run in a command line, run your Postman suite in a command line. So you can actually build in your smoke testing, you can actually deploy your software and then run an automated smoke test to make sure it actually deployed. So you don't have to do that yourself, though you probably will anyway. Let's be real. Shift security left. One of the things that I've run into a lot when going into the cloud is that as a developer, you have to be a lot more security conscious. A big part of this is that at least by default, everything is public. And so everything you deploy becomes like a zero trust boundary, as opposed to an on-prem world where your security people kind of hang out, they build a big moat around your data center, virtual moat that is, and then pretty much everything in there is fair game. In the cloud, you tend to have more of a zero trust posture, because even though you can do the same thing in the cloud, and that's what most companies do, they build everything in VNets, put them behind firewalls, just like they do on-prem. That's not necessarily the default way, at least the cloud tutorials tell you to do it. But in general, as a developer, you need to be a lot more security conscious. You need to think a lot more about security. At least I have on the projects I've been on. And so what you want to do is make sure you shift those security requirements to earlier phases of the project. Something that's a not ideal situation is when you build your thing for however many months, and then you just kind of kick it over the wall to the security people to do their pen testing thing. And then you end up with, 2 months of remediation when you think you're going to release your software next week to your customers. And so by moving that further up in the process, you can prevent that from happening and make your life a lot easier. And you get better software as a result too. So it's good for the software, it's good for the company, it's good for you. Infrastructure as code is your friend. It does not matter what infrastructure as code you use. Some people are really hype about Terraform or Bicep or whatever. If you're happy with what you're using at your company, it doesn't matter. If you're not happy about what you're using, or you're new to infrastructure as code, the default at 3Cloud, we tend to use a lot of Terraform, but we do work with Bicep and other things. Just Terraform's nice because it's not cloud specific. That being said, the folks at HashiCorp have come up with some licensing things that have made certain folks in the community a little skittish, but I don't think it really affects any consumers of Terraform. And so we don't see people running away from Terraform as a product. That being said, there are other alternatives. If you want something a little bit more C# based, you can use stuff like Pulumi or Azure SDKs, or really whatever you're into. There's a lot of ways to do infrastructure as code. It doesn't really matter, just as long as you're doing it. That's kind of the primary thing. You want to get in the mentality that your services that are deployed are more cattle, not pets. So basically, this goes back to the 12-factor thing, where you want to make your services quick to start up and quick to dispose. Because generally in the cloud, when you're building things for redundancy, you tend to build your redundancy and your availability by having a fleet of things that are relatively transient, that individual things can go down, but we just spin them back up right away. It's kind of like if you've ever read the book Anti-Fragile. That's kind of how cloud applications work. They try to be anti-fragile by having larger fleets anyway, of individually, insignificant units, but as a group, they're more available. You want to make your infrastructure immutable. So one of the big problems in on-prem and the cloud is having infrastructure that you can modify while it is in place. And what'll happen is you end up in your various environments, especially if you have long-lived infrastructure, where your lower environments will drift away from your upper environments in a configuration sense. So generally, what you want to do is when you deploy something, you don't want it to be able to change it. unless you update your code and redeploy that infrastructure, blowing away the original infrastructure. So this is something that's going to make your environments a lot more consistent. And if you're in the phase where you're trying to figure out your configuration, you're going through different changes to get things locked down, you want to make sure that you're making those changes in code so that you know what you're doing and you can promote that to upper environments. A lot of times, at least in on-prem, I've experienced where people click a bunch of buttons, kind of forget what they did, and then we have to relearn the lessons in every environment, which is ugly. And obviously, you don't want to do that. So, adopt immutable infrastructure. And again, similar to that, make sure you maintain dev prop parity. This is again straight out of the 12-factor framework, but the advantage of using infrastructure as code and immutable infrastructure is that you can maintain dev prod parity. I have been burned a countless number of times as a person building software both on-prem and in the cloud by configuration differences between environments. It is a long, I've spent many hours, and the more of that we can get rid of by making the environments as close to each other as possible, not necessarily from a capacity standpoint, but from a configuration standpoint, the better off you're going to be. Like, I've been burned in so many ways by not having consistency between the environments. And finally, you can adopt the cloud native ecosystem without going to the cloud. So this includes tools. The big tool in here is to Dockerize your applications. Because if you embrace Docker, you get access to a whole bunch of other different things that can make your life a lot easier. So that includes all sorts of tooling around different cloud functions, but it gives you access to Kubernetes. It gives you access to things like Dapper, where you can abstract your infrastructure. It also breaks away your reliance on any particular cloud provider. If you're using the cloud native ecosystem, it doesn't matter as much whether you're on a local cloud or whether you're going to AWS or Azure or Google, because all of them can run Docker containers, and it matters, and you can go to whichever one of them is most convenient for you. So adopt the cloud native ecosystem, specifically Docker, and then you can kind of move up from there in your applications. If you want to learn more about building cloud-ready applications, the number one resource for me is the Azure Architecture Center. I'm pretty sure Amazon probably publishes the same thing. I've noticed that whenever I look, the documentation tends to have a surprising amount of parity, like, they sort of copy each other. But for me, the Azure Architecture Center is great. So all those like 3-inch thick books that you're supposed to read, but probably didn't because you have a lot of other things in your life, all of that stuff is distilled at the Azure Architecture Center. Another book that's worth reading is the DevOps Handbook. It details out all the different capabilities that are part of running a generative organization, and all those things will help you build cloud applications. And then finally, if you need to prove it to your boss, go check out the DORA Capabilities and Research, which is actually on Google. Google sponsors the DORA Research, which is basically the DevOps research organization that's behind a lot of behind the state of the DevOps report. So they sponsor that, and they have a great website that goes through a lot of information in the DevOps Handbook. So finally, takeaways. The biggest takeaway here is the cloud works better everywhere. So if it works in the cloud, it's going to work in your data center, and it's just going to be better as a whole. The cloud doesn't mean AWS, Azure, Google. None of those things are particularly important. If you build cloud-ready apps, you can run them in any of the cloud providers, or you can run them in your cloud services on-prem. How many people have been following the whole David DHH anti-cloud rant on Twitter? The thing is, like, he may talk about getting away from the cloud and bragging about how the cloud is evil or whatever he's into this week. But the reality is they're trying to recreate the cloud in their data center, which is perfectly viable as a strategy. So even though they're anti-cloud with a capital C, they're still pursuing cloud technologies on-prem, which is something that you should be doing as well if you're not, company's not going to the cloud. From an architectural and code standpoint, you really want to adopt any kind of loose coupling, and you want to make sure you build in as much automation as is reasonably feasible in your application, whether that's automation around building and releasing, or automation around testing and validation, or automation around security. automation is generally a good thing, and you should be devoting a certain percentage of all of your sprints to improving the automation in your application. So with that, go forth, build cloud-ready apps. And anyone have any questions? Go for it.
So earlier you were mentioning infrastructure as a code and relatively new coding, being self-taught within the last 2 years. Could you explain more about what that looks like and what it is?
So, normally when you provision, especially cloud infrastructure, kind of the default way they show you in the tutorials is to go and click a bunch of buttons in the portal. Not ideal from an automation standpoint. So there are a variety of different programming languages and technologies that will allow you to write source code, and then that source code can be ran to build your infrastructure. So there's about, a dozen different ways to do it in Azure. Probably the most common one that we've seen in the wild is something called Terraform. So Terraform, you define your infrastructure resources using a language called HCL, and then you can execute your Terraform code in a pipeline or from a command line to spin up your infrastructure. Alternatively, you can learn PowerShell, and there's PowerShell SDKs for Azure that you can use. It's another way to do things, but generally my preference is more towards declarative forms of infrastructure as code, where you kind of describe what you want and then tell the thing to go make it, versus imperative forms of infrastructure as code, where you're basically just like giving the computer a series of instructions. But as like a newbie developer, learning the Azure CLI, if you're in Azure, would be a really good use of your time. And then learning like some basic PowerShell scripting, because that'll be really good for your side projects. And then you can learn like something like Terraform later, once you're more comfortable with just building apps in general. There was a question in the back somebody had.
So you mentioned the commutable infrastructure.
Yeah.
So what kind of in Azure environment, in your experience, what kind of technologies have you used? I know Azure blueprints were there forever in preview. What kind of technology do you use to stamp down configuration?
It's more of like a configuration of permissions. So in environments that are, in development, whatever, let people fiddle around. But in your upper environments, you want to make it so that the only thing that can change your infrastructure are agents that run in pipelines. So it's more of a permissioning thing rather than like using Azure blueprints or some other thing. As a general rule in production, you don't really want anybody to have any kind of ability to change anything as a general rule. That being said, they do have there's the concept of break glass permissions, where people can be given temporary access to production to do things in the case of of fire. But as a general rule, anything above like your development or sandbox environment, you don't want to have people be able to change those configuration values in the portal. Any other questions? All right, go for it.
You mentioned the security scanning for your, I think in the context in the CI/CD pipeline.
Yeah.
Making sure what do you use, it static code analysis, or how does that?
There's two different kinds. There's the static code analysis, and then there's stuff for deployed code, or black box versus white box. Generally, a lot of companies that I've worked with have adopted static code analysis. And there's a lot of different tools. And of course, I can't remember them all off the top of my head. The one I'm most recently working with right now is one called Checkmarks. But there's Veracode and things like SonarQube. SonarQube is free versus some of the other tools which are paid. But SonarQube is more code quality than security. But it does have some basic OWASP type top 10 type of security scanning built in. So if you're looking for something to do on more of a personal level to experiment with, SonarQube is probably a good option, versus in a company, most of the time there'll be some expensive enterprise grade security tool that you'll just be in charge of integrating into your pipelines. So where I'm at right now, we run a checkmark scan on every single build. So every time we build the package, we throw up a checkmark scan to make sure nobody's engaging in any shenanigans. So far, so good.
So is it checking the code, or is it hitting the site to scan for want to do?
Static code analysis checks the code. So it's similar to like a linting tool. So if you use ESLint, it's kind of the same deal. Also, you can static code analysis your infrastructure code as well. So there's the Azure TTK for Azure and Bicep code, or ARM and Bicep code, and I think there's a similar tool for Terraform, or there's similar tools for Terraform. I haven't messed around with those yet too much, but and then there's also your app scanning tools like the ones we talked about before. What else we got? Any other questions?
So
Go for it.
earlier you were mentioning ETE and smoke. For smoke, is that just automated type or automated API testing?
I mean, it can be, but it's also just knocking on the front door of your website to make sure it's still working. It's basically the equivalent of what a human would do when you deploy something and you go and you like log in and click through the screens real quick, make sure the app didn't blow up in your face after you deployed it, which I'm pretty sure all of us have done. It's basically just writing a script to do that for you. Especially in the case where some people don't do their smoke testing as often as they should, myself included. I don't automate because it's important. I automate because I'm bad at doing things consistently. So we make the computer do them instead. Because I'm a fallible human. All right. All right, with that, that's all we got for today. Thanks for coming out, and we'll see you at the next one. Should have hidden that little bar.
Jason. Huh? Oh, I didn't get a chance to look because I was trying to get it. We had a little challenges getting the teams sharing with this, so I didn't get the chance to check the numbers on it. I don't know. I was just lucky to get it to somehow work. It's going to be kind of sketch, but at least we have something. And next time I'll know better because it's like at a Teams.
Oh, right.
Oh, I'm still sharing here.
What's funny is I totally went back into my house to get my adapter because I forgot to grab